Oops. I've been told by living lifestyle. Hotel rich show me very well. And it really hurts. Try yourself and your soul. It's the price you pay for rock and roll. And no one understands it, how you feel. For it's so real. Oh, it's so real. Baby, don't you cry for me. It's an illusion, just an illusion. I thought I knew what I should be. It's an illusion, just an illusion. Critics crucify your show. Another drink and then you lose control. And then on stage I feel a fire burn. There is no return. I'm always I feel like every week is like a new week. Well, every week is a new week for sure. And it's always, sometimes I feel like weekend is something that really like a maze in a way that after the weekend you start to forget everything you learned from the previous week. So one of the examples that I can give you is like this morning that when I am looking for something in my backpack, I feel like that, oh shoot, I forgot the receiver of my microphone. So for those of you who are on YouTube today, sorry about that. The reception of my voice wouldn't be that great, and I'm trying my best to be as loud as possible so that you guys hear. But if you're here live, you're lucky because at least you can hear my voice clearly. So, and I understand that, like even though even I forgot the procedure that I used to have every week, right? So it's always a good thing that before we start a lecture, try to refresh your mind, try to put those stuff into your cache again, so that when you learn a new context, you will at least have something in there So no compulsory miss anymore, right? There's only conflict misses. So, well, the reason why we are talking about cache is because the performance gap between the processor and memory is so huge in a way that if you don't deal with that properly, it's almost impossible for your processor to work efficiently. So we build memory hierarchy in such a way that we incorporate some small amount of SRAM caches. They are expensive, but if you make them small, it's affordable. And for the SRAM caches, we typically organize them into multi-labels. And the closer to the processor, the smaller the size. And the reason is because smaller the cache, the access latency could be as short as your processor cycle time. But in the meantime, we also don't want the things to go over the DRAM almost most of the time. So we try to build multiple labels of caches. So we have some larger caches behind your first label and the second level caches to make sure that most of the time your request will be satisfied by the DRAM instead of a lower level memory hierarchy. So that's the idea of memory hierarchy. So with this memory hierarchy, what happened when we read the data is that, remember, with the memory hierarchy, we always consult the first level of the cache before we consult others. So only if the stuff is not found in the L1, we will go to lower level memory hierarchy. And same thing, a similar procedure for writing data. The only thing that is different for the modern write-back cache is that we will set a 30-bit associated with each block if the data is modified during the write process. So that's what we learned, and based on those basic information, we definitely learned a lot. We know how to simulate the cache, and we know there are tons of cases that your code may be underperforming because you are not optimized. Your code is not fully optimized for cache performance. So we introduce a few hardware techniques, for example, prefetch to reduce compulsory miss. We also talk about write buffer to that the write process, allow the write process to respond to your code earlier so that your processor doesn't have to wait until all the write process finished. And we also introduce the idea of banking and pipeline to make sure that whenever you have a miss, the miss penalty can be addressed in a more elegant way that your latency won't be that big. And critical word first, early restart also follow the same philosophy that we want to allow the processor to continue execution as soon as we can. But as you can tell, those hardware techniques, only prefetch can help compulsory miss. However, others only address the miss penalty. So it's not as effective as software optimization. So if you can carefully lay out your data structure, like the demo I showed you in the last week, just by arranging your data to make sure that it's better aligned with your memory alignment, or say your underlying architecture, you don't need to do anything, but you can reduce the footprint of your program. So in this way, you can improve capacity misses for sure. And also, another thing which I didn't mention, but thinking about this, right? Not only the capacity miss, but also the case that if you have fewer amount of blocks that is necessary to store data structure, it also means that you can potentially reduce the amount of conflict misses, even though your data is not exceeding your capacity of your cache. And also, the other thing to think about is that most of the time, software programmers, we are romantic, so we just want to write code that looks good. But looks good doesn't mean it works good, right? So make sure that when you write the code that satisfies yourself, not only satisfy yourself, but also satisfy the access pattern. So sometimes you may think, well, this data structure looks so beautiful, it's like an art, right? But unfortunately, when you put this art into practice, it's like a disaster. So one of the examples, which I'm turning off my mic right now, is that a few friends of mine who graduated from MIT, and not sure how many of you know the CS building of MIT. If you don't know what a CS building of MIT looks like, definitely search Google online and you will figure out, well, that's actually an art. But the thing is that my friends working in that building tell me it's a disaster because the shape of the room is never square, and some of the angles they do have the reflection comes in, so sometimes some of the room is always hot. And most terrible thing is because one of the roof is not is actually inclining into the building, so whenever there is rain or snow, the water just flow in, and because they are so heavy, you can never stop them from leaking. So those are so even when building, there are cases like that, right? So don't write code like that. And also implementing algorithms in a more cache-friendly way. So sometimes it doesn't. So here, looking at the word implementing an algorithm in a more elegant cache-friendly way. So I'm not asking you to significantly changing your algorithm, but thinking about how to implement in a more elegant, more cache-friendly way. So today I'm going to show you an example on matrix multiplication. And first of all, a lot of cases you might be asking me, hey professor, how do I know? Like you told me that, well, I have to figure out the underlying architecture, but my question will be, how do I know my cache configuration, right? So here I'm showing you, like in many situations you can know this, right? And here I'm giving the example of Linux system. Like I can do get conf -a, and I just need to. This would actually give you everything about the processor architecture. But if all you need to do is cache, just grab the word cache. And you will figure out, well, it actually tells you this, right? And if you didn't learn the computer architecture, this is like a set of magic words. But now you can guess, right? Like level 1 iCache means instruction cache. The size is 64K for this processor. Weight associativity is 4. And the line size is actually the block size. So it's 64, right? So you can tell, like for this processor, this is an AMD Ryzen processor. So the L1 cache size is 64 4-way, and the data cache size is 32 kilobytes and 8-way. And if you go to level 2, is 512K, 8-way, 64 byte. And if you go to L3, wow, 16 megabytes, right? And let's look at another processor I have. Come on. Hello, are you there? Are you there? Are you there? Is it died? Is it dead? No! Are you there? Okay, let me try another. Okay, this one is alive. What happened to my machine? Okay, I can still do this one, right? And this is an Intel processor. So see, the interesting thing here is that Intel processor is iCache is only 32 kilobyte, but it's an 8-way cache. And as I told you, right, so a few things that I can tell here, but since the grad class, I can talk more. But typically, instruction cache is more important than data cache. Do you agree with that? Because we need to access instruction cache for every instruction, but not for data, right? So the timing of instruction cache is actually more important than the data cache. And again, because Intel's foundry technology is a lot better, so they can make an 8-way cache in their level 1 instruction cache. So, and the thing is that, well, even though it's 8-way, right, but it's only okay. Why not this line? Maybe I will receive later. Okay, so the thing is that because their process technology is better, so they can make 8-way cache as fast as their processor. But as you can see, for the AMD processor, they can only make it 4-way, right? And the thing is that if you read the textbook carefully, there is a graph showing that 8-way 32 cache is almost equivalent to the miss rate of 4-way 64 kilobyte cache for a variety of reasons. So but in the meantime, 32K cache is way smaller than 64K cache, right? So if you are the hardware manufacturer, you definitely want to make smaller cache with higher weight associativity, if given the clock rate can be the same. So this is also another evidence showing you that the process technology of Intel is way better than AMD in this way. Well, and also this processor they have a lot of tweaks so that they only need this amount of L3 cache to achieve similar levels of performance. Okay, so this gives you an example, but what happened? Okay, my machine is back. So this example gives you how you get the cache performance of your code, and of your processor. So now, given you know this, right? At least you know that each processor now has like a 32 kilobyte L1 data cache, and today, the behavior of data is easier for you to figure out. So the first case study I'm going to show you is on matrix multiplication. And this algorithm, some of you might have already heard it. It's called blocking algorithm. But before we talk about blocking algorithm, let's take a look of this 3-level nested for loop. Well, given you are in a grad school, right? I don't think I need to explain too much about what this piece of code is doing. So my question is that, well, what's the complexity of these pieces of code? I was expecting everyone. Oh, n-cubical, right? So it's an n-cubical, right? So now if I tell you when n equal to 1k, it takes about 1 second. Can you kind of like estimate to me how long does it take for n equal to 2k?
Don't we need to track it?
What?
We need information about how the cache works.
Well, before that, right? Assuming that you don't know cache, you only know algorithm.
Oh, that's
4?
2.5.
2.5? This is like Price is Right. 8? Okay, right? So typically, if it's an n-cubical, you may think it's 8, right? So now, let me run this pieces of code for you. So, let me see. Matrix. I hate this keyboard. Okay, so this is exactly the matrix multiplication code. Like I make it a separate function here so that the compiler won't do some weird things. So here is the matrix multiplication, right? You compile it. Now run it, right? And this is for 1K. Oh. Okay, 1K. It takes exactly about 1 second, right? Let's run it for 2K. 8 seconds, huh? Let's count. 1, 2, 3, 4, 5, 6, 7, 8. I feel like I'm a personal trainer now. Okay. Not yet. Not yet. Not yet. Not yet. Not there yet. Not yet. Keep going. Hang in there. Okay, 28 seconds, right? What does that tell you? Right? Drop the algorithm class again, right? Like the complexity estimation doesn't even work out. So the thing is that, well, in a lot of cases, you saw that your program performance is going to scale with your algorithm complexity, but that's not the reality, because now you know, right? Like a lot of you know there's something called cache, right? So definitely something is wrong here. So what's wrong here? So as we mentioned, right? No matter it's a Core i7 or AMD Ryzen, right? I just show you that the data cache is only 32 kilobytes. And now, if each dimension of your matrix is 2K, and thinking about this, right? 2K, and you have 8 bytes in each element because it's a double array, right? So each row itself would take 16 kilobytes, right? And now, if I'm doing matrix multiplication in this conventional way, what will happen is that to calculate the result of C, I would take one row from A and one column from B. And remember, each row takes 16K, and each column also takes 16K. So when you do this, even though, well, let's ignore other factors. Just those effective elements you are calculating is already exceeds the capacity of your cache. Do you agree with that? The capacity of your cache already exists. You can only hold at most 2 rows and columns for each time. What does that mean is that, what does that mean is that the next time when you are iterating over the next combination of ij, there must be misses. There must be misses, right? So it turns out that when I am doing ij, when I increment my j, I'm reusing this row, that's fine. But for this column, it's a completely new thing, right? And apparently, because you only have 32K, right? When you fetch this 16 kilobytes of element in, you must kick out something. So the cache hit rate is actually pretty bad. So to figure out, and the next time when you go to the next I, you'll figure out because the previous columns are all kicked out, right? So there's no way that you can keep all of them. There is no way that it could be a hit in this case, right? So the performance is terrible. So how bad is the cache hit rate? There are a few tools that you can use. One of them is called Valgrind. Many of the and Valgrind is actually a pretty common tool that I think it has multiple platforms. Like you can download. You can download its source code, and it builds on Mac, it builds on Linux for sure, and not sure about Windows, but at least you have these 2 platforms. And now let me just show you that for do I really need to do this? Okay, so for Valgrind, so Valgrind, as you can see, right, it gives you, whenever you run a certain pieces of code, it will start to generate stats, and it will tell you how many caches are misses, how many cache accesses are misses. And for this pieces of code, the reason why I didn't finish it, first of all, right, the raw program itself takes 28, and the thing is that Valgrind use emulation method. So when you run a program with Valgrind, what it actually does is that it instrument the code and capture all the memory accesses and try to build a cache simulator like what you did in the class, but in program, and figure out how many of them would be misses or hit, and then generate the states. So as you can imagine, this it's really slow. And another tool that, but even with this slow tool, it kind of like tells you that, well, at least we have 20% of them are misses, right? Which is like a significant number. And now I'm telling you another tool that could potentially be more efficient. That's our old friend perf. So in contrast to Valgrind using a simulation method, perf just leverage those performance counters in your that is now pretty common on your processors. So what it does is that it just read the initial value of those performance counters and compare against those values after you finish the program. So it's just subtraction and collect the stats at the end. So it's pretty efficient. So use perf, you can use -d to get the memory-related stats of your program. So now let me run this. Oops, perf. It's not there. Oh. Okay. So, well, this would run probably about the same time as the runtime of your matrix multiplication program. But after finishing it, you can at least see a lot of stats that are memory related and to see what's going on there. And as you can see, this program really takes a long time, even though I'm trying to think about what to say at this moment. It's still not finished yet. So it's definitely not a good friend for me as a case of demo. And finally now, right? So, okay, so here you can see like for the L1 cache load misses. So this wording is misleading. It's actually the percentage of all cache accesses. So what it tells you is that 20% of okay, so if you divided this, right? This is the amount of L1 cache misses, and this is the amount of L1 cache loads, right? So there is a total of about like how much? 50 millions of loads, and only 10 millions of them are 10 millions of them are misses, right? So the miss rate is also about 20% in these cases, right? So it's pretty high, right? Thinking about the math you just did previously. So that's why the performance is so terrible. So now, let me introduce another way of implementing the same algorithm. So the most naive way of implementing this matrix multiplication algorithm, if you ignore the fact that you have caches, this is the most intuitive way of no objection of that. It's easy to understand. However, as you can see, the performance doesn't scale with your problem size. So a better way of doing this is actually making your left-hand implementation to be the right-hand side. So what the right-hand side is doing is that, as you can see, right, we got a triple amount. We got 3 other nested loops in there. And the basic idea here is that, okay, instead of treating the whole matrices as a big one, we partition the matrices a few subblocks, and then every time when we do matrix multiplication, we only do subblock accumulation and accumulate the result in the future, right? So that's the idea of matrix block algorithm. So let me show you the animation how we do this. So with the animation, this time, as we said that if we partition, so now assuming that we partition this matrix into 4 different pieces, what would happen is that in the first run of the iteration, right, when we calculate the C, instead of calculating the whole row and the whole column in A and B, we only perform submatrix multiplication on part of the A column, A row, and part of the B column. So because they are smaller, so you can imagine both of them can fit in a cache. And when we iterate through the next element, instead of fetching the whole column or the whole row, we only fetch part of the column in B. And another thing that is also interesting to see is that if you remember, right, the block, every time when we fetch data, it's in a block manner, right? So if your data access pattern is in a column, it's very unlikely that this item would if you always fetch the whole column, when you fetch this item, right, it's very likely that because the limited size, it's very likely that this one is going to be kicked out, right? But now, if you do this in this way, these two may both presented in a cache at this time. So this could be a hit. This could be a hit because now when you fetch this column, right? Remember, this partial column. Remember that when you fetch this element, you also fetch this line of elements, right? So this one could also be a hit, right? And now when you navigate, go to the next element, also partial column, right? Similarly, partial column, right? And if you partition the column, the size of a column and the size of a row in an appropriate way, it's very likely that they are all in a cache at this time. Now, when we advance I, again, because we are doing it in just a submatrix. So the advanced I, well, for this one, we definitely have to fetch the next column, next row. However, the other columns, they will all be in a cache at this time. So the cache performance will be way better than what it used to be. So this is the idea of block algorithm. Because now, every time you only need to fetch, keep the some matrices in your cache. So how good is that? How good is that? Let me run a demo for you.
Is n the cache size in the base code? Well, in the optimized code that you showed, is n? You said array size over n was n the cache size, or
Which one?
uh,
Oh, this is the amount of partition. So saying that if I want to partition the subblock into 4 different pieces, right, the n will be set to 2. Okay, so now let me show you the demo I have. So I have a blocked version of the implementation, right? So this is so this code takes one additional argument, which is the n that you mentioned for each dimension by how much by how many partitions we are going to partition it, right? And for this implementation, right, you can see the matrix multiplication part is exactly the same as I show you. So now let me run the plain version for you, right? So for block MM, if I have 2K by 2K, and if I partition each column and row into 256 pieces, meaning that I will have 256 times 256, this many subblocks when I am calculating the matrix multiplication. How much time it takes? 8 seconds, right? It makes the magic of algorithm complexity works. Do you see that? Right? So the thing is that algorithm, the complexity works well if everything fits in a cache, right? And well, we can use perf again to see what's the cache cache performance now, right? So if you use perf, right, what it shows you that, well, right, most of the, here we go, right? Only 1% of them are cache misses now, right? Previously it was 20%, but now only 1%, well, 2%, right? So 10 times reduction, significant performance gain, right? And of course, well, and it's kind of interesting to play with the partition. So if I do it in 128 pieces, do you think it's going to be better or worse? Well, it's better, right? And if you, yeah, I can further partition it in like 512. Is it better or worse? Worse, right? So it's also interesting that sometimes you need to run several. You have to figure out what's the best configuration of that. And the one thing interested that I can share with you is that it's somewhat related to your cache block size, right? So if you can make sure that your row or column, they are better fit with your cache block size, then the performance will be better. Okay, so here's the example, right? So now you show, well, I didn't ask you to to change the algorithm, the basic idea of the algorithm, but when you implement it, if you can block it to make sure that every time you only do partial updates, the performance could be a lot better than just naively implementing it, right? So that's the block algorithm. So now I'm asking you this, right? Why the block algorithm make the cache miss rate better? Okay, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, let me see. What do you guys think? Okay, so most of you think it's D, some of you think it's C or B. So I guess it's probably worth a while that you guys discuss with your friend again to get a consensus of what's wrong or what's right, or maybe you will figure out both of you guys are having some misunderstanding about the case. So again, 90 seconds, think again, let me know your answer. That's what I'm saying.
Those actions you're running out in apps or something. You're coming like yeah. That's the action. We all agree there are no, it's not. Yeah. Yeah.
All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, wow, so most of you now agree that it helps with the case where both capacity and conflict misses. And can someone explain why? Okay, you're my friend.
It's capacity misses
Mm-hmm.
because sometimes we run out of space in the cache, so we have to replace it with we have to replace a new item with something that's going to be used again.
Mm-hmm.
And then it's a conflict miss because after so many integers, the tag, or is it the index? Okay, one of those two overflows back to 0, and then we get a conflict miss.
Right. So there are two folds of the reasons behind this, right? First of all, part of it is just because your row or a column, well, is so big, right? So you cannot put both of them in there, right? And all of them in there once at a time. But if you make it partition it into submatrices, and if you partition them in a way that makes sure that each submatrices that you are going to calculate it fits in the cache, then you can definitely reduce the case of capacity misses, right? Because each submatrix is now smaller than your cache capacity. However, in terms of conflict misses, sometimes even though we are just calculating like two columns, right? Because the fact that you are going to because you have limited amount of cache ways or sets. So you know that we are organizing your cache in so say that you have a 64 kilobyte cache, right? And we organize them in 8 ways, then which means that each way can only store 8 kilobytes of data. So there's no way that you will be able to put a row or a column or 2 rows or a column anyway, because each way is not the capacity of each way is limited, and definitely when you fetch the new one, it will kick out another one, even though sometimes they belong to the same row or column. So this is also this is some kind of conflict misses that we can address through partition the algorithm into submatrices. All right, so great. Now, another thing that if you start your assignment to, you must see this matrix transpose, right? And now I'm telling you, this is also another thing which compiler won't do for you. You have to do it. Remember, there was a case before that we say we improve the CPI of a certain pieces of a code by adding a sort in front of it, right? Like if you pre-process your data in certain way, then that will make the performance of your code better. So here the magic that I'm telling you is that, you can add matrix transpose in front of matrix multiplications. So, okay, if someone is teaching you algorithm, it will definitely tell you, well, this is adding redundant operations. But from the architecture perspective, I'm now showing you a demo, right? So I have a block mn transpose.c, which I also explicitly run this pieces of a code. I made another transpose matrix BT, and the transpose matrix, this one would transpose the B matrices before calling the block mn function. And because I am calculating on the transpose matrices, so I have to change the order of multiplication, right? So this is what the code is doing, and let's see how good is the performance. Again, if it's 2K, and I remember we did the best with this configuration, right? So let's run it and see how much time it would take. Well, about the same. Well, remember it was previously 6 seconds, right? But now, even though I add the transpose code, which you think adding transpose would make more, would create more operations for the CPU, for the memory. However, what you see here is that even with those redundancy, my code is now faster, right? So the follow-up question was is that why? Okay, give me a second. I think doesn't lock properly. Okay, this. Are we still? Okay, here we go.
Joe. Oh, excuse me.
All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. Wow. Okay. So let's still have a discussion, and let's see what you guys think.
So let's say we take the example we make it so that the PT actions and see if we go row by row. index has to go to having then the path. If I have to read it and use the
All right, looks like you guys are quite calm down. So why don't we wrap up the discussion in 10 seconds?
No.
5, 4, 3, 2, 1. Time is up. Okay. After discussion, majority of you think it's C, but there are also quite a few of you think it's E. So look at this. Okay. So how about compulsory misses? Are we helping that part? Are we helping that part?
No.
Not really, right? Because the definition of compulsory misses is that the block never exists in a cache before. But what would really happen is that whenever you fetch a sub row in the B matrices, a sub row actually brought in several elements, and the several elements include all the first element in each column in the sub matrices. Do you agree with that? So compulsory misses for this part, there's nothing changed in there, right? Because those elements were originally there in the first accesses, right? So it doesn't change anything regarding the compulsory misses. How about the capacity misses? No, right? Because you didn't change the submatrix's sizes after the transpose. But why is it still better? Because of the conflict misses, right? Remember the previous access pattern. When you performing a matrix submatrix multiplication, you are multiplying on a column, a row, and a column, and thinking about the memory layout of blocks, right? Each column actually was striped across many different blocks. However, after you transpose, you are actually doing row by row multiplication. And each row is already, each row, they all exist in the same block. Right? So the fewer the blocks you access across the computation, it means that the fewer chances you are going to have conflict misses that kicks out other items when you are performing. So that's why the performance after matrix transpose is better, even though we added this overhead. Yeah.
This optimization aspect should also remain increased because we introduce the new array and B2.
That is also possible. That is also possible. So it potentially access, well, if you count the amount of compulsory misses, I do believe it's increasing. Right. But the question is asking remove.
Yeah.
Right. Right. But you are right. In terms of compulsory misses, this one is actually making it worse. But the majority of misses here is coming from conflict misses. So matrix transpose actually help us to address. So it's an interesting study, right? So it adds some overhead, and it does make some case worse, but the benefit of doing matrix transpose is way better than the disadvantage it brings. So this is a worthwhile optimization. And again, right, the compiler can never know this, and compiler won't do this for you. Only the programmer know we can do matrix transpose safely, and you have to change the way how you multiply it, which the compiler can. Oh, right. Last thing that is interesting to talk about. If you remember last week, we talked about a hardware technique called prefetch, right? In Noam Joby's paper, we also mentioned that the hardware can do prefetch. And in fact, there exist instructions to do prefetch. And that's called, and if you use this is called software prefetch. So we talk about matrix transpose, right? We can actually, let me see, what else do I have? Oh, see, I keep having optimization, right? So matrix transpose. Now, this example, we know matrix transpose itself is an overhead, and you actually have a very good observation. It increased the amount of compulsory misses. So now, as a software programmer, I'm aware of this issue. So I add prefetch instructions to fetch those data earlier so I can eliminate those compulsory misses. So how can I deal with, so here, right, I added an instruction here. Whenever I am doing stuff on this BII, BJJ, and KK, before that, I fetch the next row, right? So let me do this. So let me run this prefetch. Wow. Run this prefetch version of the code. It was 5.3. Okay, doesn't help that much. Let me run this configuration. So this is the slower configuration. Let's see. Okay, 7 seconds. Huh? I don't see it's working here. Let's see. Let me run it for several times. Okay. So actually this processor is... Okay, so now let me do it. Huh. Seriously? Let's try another machine. Okay, so this is an example tells you that prefetch doesn't always work, right? Here we go. There is another example I have. This is simply the transpose code. So this one, okay, this one I take. This is a C++ code. I am doing some transpose under a big chunk of matrix data like this. And let me see. For this one, transpose, right? And this is the transpose for not. This is the original version for not doing any transpose. Sorry, not doing any prefetch. But now let's do prefetch. Right? As you can see, slightly faster. right? So prefetch is somewhat interesting. First of all, software prefetch works in a very limited degree. And the second thing, which is another demo I'm showing you now. So this is the same pieces of a code. And I'm going to run it on a different machine. Demo memory fetch. Okay, so this is the transpose. So the same pieces of a code, the same binary, right? So this one on this machine, well, 1 second, right? And now do a prefetch. See, for this processor, using prefetch is actually slower, right? So prefetch is kind of interesting, and it's also complicated in a way that. So first of all, remember when you do prefetch, it issues those requests earlier. So what would happen is that, and where are you going to put your prefetch data? Still in a cache, right? So there are cases where if you prefetch stuff, it does help address the compulsory miss. However, when you put those blocks into your cache, because it still needs space to store, so it has to kick out something. So it causes more conflict miss afterwards, right? If your prefetch is not doing properly. So prefetch is like a two-side play. It helps address the compulsory misses, but sometimes because you need space to store those prefetch blocks, so it would hurt performance in some sense. So that's the first demo when I do matrix. When I try to insert prefetch in matrix multiplication code itself, it doesn't work. And for the second pieces of a code, you see the first part of the demo. I ran the code on an AMD processor. And when I insert prefetch, it works, right? The prefetch does give you better performance than not prefetching it. But now, when I log into another machine, which is an Intel machine, the prefetch actually make the performance worse. Why is that? Can some of you make a guess? Overhead? Well, but why prefetch is an overhead in the second case, but not for the first case? The size of the sensitivity.
The miss penalty is
Miss penalty, size of cache associativity, clock rate. Okay, so here's the thing, and the answer is actually in this slide. The processor also do power prefetch. And the smarter the hardware prefetch mechanism is on a certain processor, the less the less benefit coming from the software prefetch. So the truth is that, so this is also a very good example, tells you how smart each processor's prefetch mechanism. So apparently, in the first case, the processor's hardware prefetch isn't that smart. So your programmer's prefetch can still help. However, for the second case, the processor already do a super awesome job in prefetch. And when you add those prefetch instructions, it just creates overhead.
How are you supposed, like, how is you as a developer supposed to know whether the CPU is running the hardware prefetch?
So every processor has the hardware prefetch now. It's an automatic thing that you can not even turn off. So you should be aware of that. So prefetch is kind of like it used to be a good technique to use, but now I would say this is an interesting mechanism. Most of the time, I don't think software programmer can use it in a right way. But because it's difficult, so it also makes a case that a good project for a study. So our term project will be somewhat related to that. And I will release the detail by the end of the week because I'm still working on it. Okay, so just give you a few idea about what prefetch is so that you won't feel like completely like shocked when you see that. Okay, so again, we talk about software optimizations, right? And those software optimizations, it helps you it helps us to address those cache misses ultimately. And those are the things that none of the hardware techniques can help. All right. So now, to make this class less hardware oriented, let's dig into the code. Right, so this pieces of code is actually a pretty simple C code that I have an argument called dimensions, right? And user can input a dimension, and whenever you give us the dimension, it will allocate a two-dimensional array, dynamically allocated two-dimensional. And the size of the two-dimensional array would be the type of your data and the dimension squared. Right. So if I have a 70K dimension in one dimension, then the total data size will be 32 gigabyte, 37 gigabyte. Now I'm asking you, for these pieces of code, what would happen if I run this pieces of code on the machine with 32 gigabyte, which I'm going to start running it now. So this is the machine I have, right? I have 32 gigabytes of memory, right? And then, what?
Yeah.
Only 32? Yeah, I'm a poor guy. Sorry about that. And now I'm running. Wait, I thought I have the demo somewhere. Oh, okay. Now I'm running this pieces of code. Memory allocation exactly the same as what I show you, right? And then the dimension is the argument here, and then I will going to allocate them, and I'm going to put random numbers in there. And as you can imagine, random is a very slow function code, so it would take a while. So that's why I'm starting running it. And before we have the second round result, I'm not going to show you if what happened with it, right? But now I'm going to run it. So this is the dimension, right? Okay, I'm running it. I'm not going to tell you what happened. So now, based on your judgment, your own judgment, what's the answer of that? What's the result of that?
When the OS does a context switch, does it prefetch the cache?
When the OS does the context switch, you will have to flush the cache. But when you say, does it prefetch the cache?
Like the next process.
So the OS doesn't prefetch. Only the processor sees the access sequence it prefetches.
Every time the OS does a context switch, do you have a bunch of compulsory misses after it switches back into the process?
That's a good question. So for those misses, how are you going to categorize them? It's Okay, so when people define compulsory misses, conflict misses, they were not taking the case of context switches into account. So there's no strict definition about compulsory and how to distinguish this kind of misses when context switch is involved. I would say both of them would be valid. Because if you think about compulsory, right? When you context switch, it's a cold start. But if you think about in the long term, this data were originally there. So they could be counted as conflict misses at all. But I don't think the original definition of compulsory conflict misses were taking this into account. Okay? All right. So now I believe most of you have an answer. So wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. What? Okay, so most of you think it's D. What's D? Okay. The program will finish without any issue. Why do you think that?
We'll just have a lot of page swapping. It won't cause any
Okay, what does that mean?
lots of misses.
When you say there is page swapping, what do you assume? What do you assume? How come you have swapping?
Because there's more. There's 37 GB in the array, but we only have 32 GB physical memory. So we need to occasionally switch between the disk and the main.
Okay, so here's the thing, right? This program finishes without any issue, as most of you said, right? But why is that the case? Why this program can finish? You don't have that many memory.
Because it has an illusion that it has.
It has an illusion, right? Just an illusion, right? This is actually the hint I give you in the very beginning of the lecture. The song we play is called Just an Illusion. Right? If you missed that song, watch the YouTube video once again. The song is indeed Just an Illusion. I love that song, by the way. Right, so Just an Illusion, right? So there is an illusion called virtual memory. So I physically have 32 gigabytes of data. However, the operating system created an illusion called virtual memory, and the virtual memory actually does what you said, swap in, swap out between the secondary storage, which is the software support for that illusion implemented by the operating system to make sure that your program can still run. Right? So that's the idea of virtual memory. Okay, so now let me ask you the second thing. All right, okay, so for this question, this program will finish without any issue. So you are aware that there is virtual memory, right? Now, another pieces of a code. Okay, I have this program. So what this program is doing is that, well, I create multiple processes. And for each process, I create multiple processes, and for each process, but when I create multiple processes, I can use fork. If you don't know what is fork, next quarter there is a class called CS202, still taught by me. I can tell you more about this if you are interested, right? But now just accept fork is a function call that will create a new process that executes the same content as this pieces of code. So you will have multiple instances of this as a new process in this computer. And for this process, what it will do is that for each process, it will print a process ID. It will print the current value of A and the address of A. Okay? And sleep for 10 seconds. Print that value again. Okay, so now the question is that go through this pieces of code. Tell me what's the output. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's see. What do you guys think? Ta-da! Okay, it's a very diverse answer. So definitely, I know you guys want to talk with each other. So why don't you go ahead for the discussion? And there is some technical issue here. So what you need to do is that you can clear your previous selection and then reselect it again. But please discuss right now.
Like they're different, but they're the same. So it's gonna be one and. No, some instances both will be the same value. Yeah. No, address. No, because it's gonna print out the virtual memory, not the actual physical disk space, right? Because each process thinks it's running on an ideal list. So I think it's like they're running on different addresses, but on the same address. I don't know. What does it exactly mean by address? How is it printing out? Yeah, but it's different.
All right, let's wrap up in 15 seconds.
I see arguments.
5, 4, 3, 2, 1. Time is up. Okay, after discussion, so still C and E. So here is what we need to do. We need to do a demo, right? Because seeing is believing. So now what I'm going to do is that let's run it, right? So now I created 4 different processes. As you can see, for the first run, each process have a different value of A. And the address of A are all the same. This is the address of A. And what's after that is that every process still preserve its previous value of A. And the address never changed. Right? So if you look at this, right? What's the okay. This is the demo, right? I run it on a different machine. It also shows the same thing, right? All the same addresses of A, different values of A, right? So what's right? So
the same address is the same. So first, right, each instance will print a different value of A. So C is the right answer, right? But why is that? Why is that?
So I know what one is. Oh, okay. So one, they're running on different places in physical memory, but they're running on the same place in virtual memory, and
So they have the
program
yeah.
the virtual memory,
Right.
but it
So
makes it
so you point out a very good thing in your answer, right? So but if I want to shorten the answer into 2 words, what's the 2 words?
virtual memory.
Yes, exactly. That's virtual memory. Thanks. Right. This is the 2 words I want. So the reason why we have that is because we have virtual memory. So virtual memory is an abstraction that created by your operating system. First of all, you see we have 2 use cases. The first use case is that if you have a program that needs more than the physical memory you install, you allow the program to continue execution. And the second case is that if I have a single program that will be launched in multiple instances, with virtual memory, I can make sure that each instances still have their own space to work, right? Even though they are clones, right? Even though they are twins or triples, right? Each of them is still an individual human, right? So they would have their own sauce, they have their own space to work with, right? So that's the virtual memory abstraction. 2 big benefits that we can have, right? Like you can have each process working in its individual space without worrying about interfering with each other. Even though both of them would surpass the size of your physical memory, the virtual memory still make it happen. So what virtual memory really does is this, right? So we have multiple programs, and I create a virtual memory space for A that present an illusion that you have this amount of memory, and for another program, I also present an illusion that you have this amount of memory, and then everything is just an illusion. So when you need to use it, I dynamically allocate. When you request it, I dynamically allocate the data into physical memory. However, when I'm running out of physical memory, and as some of you already pointed out, I use the idea of paging to swap in, swap out the stuff between my physical memory and the space that I'm hosting those data for virtual memory. So this is the basic idea of virtual memory. And if you want to learn more about this, again, next quarter, CS202. And so this is, and again, right, if you're running out of space, then there is something called swap that helps you to keep those pages. So this is the basic idea of virtual memory. Now, what happened in the previous demo case is that for processor A, even though it's the same virtual addresses, because the virtual memory abstraction will pointing in them to different virtual address space, so they will have a different mapping between the virtual address and the physical location. So even though process A has and process B, they both have these addresses, they will be translated into different locations, physical locations. Okay, so what you can hear is that virtual memory is actually an abstraction of available memory addresses for programmer software programs. So this is the illusion, again, an illusion created for the programmer, for the software. It doesn't represent the real memory you install. And with that illusion, all the programs, when we compile, the addresses are using virtual addresses instead of physical addresses. And it's the operating system and the hardware work together to handle the mapping between virtual locations and physical locations. And virtual memory actually organizes memory locations into pages. So, as I said, right, the reason why we have virtual memory is that if you have multiple programs, you can now safely share the same physical memory. And also, even though you have programs that surpass the size of installed physical memory, it will still work, right? So this is why we need virtual memory. And the idea of virtual memory abstraction is like this. I still have the processor to access, to execute a program, But when I need to access the data or an instruction, remember everything is in virtual memory now. So you need a mapping table, which in operating system called page table, to tell you which page contains the instruction or the data that you are accessing, and then that page table will tell you the location of your requesting data in the main memory and fetch the page from that memory location through your memory hierarchy, right? So as you can hear, I feel like this idea is similar to something I heard before, right? So you can imagine the virtual memory abstraction is actually a software version of caching in a way that you treat virtual memory as the synchronization point of all your data. And main memory is now just a cache of your virtual memory space. And so this idea is, so you can analogize this in a way that the block size is now the page size in your page table, in your virtual memory abstraction. And the page table is like the tag array in your cache that tells you where my data is, or if my data is in the cache or in the main memory or not. And unlike the cache is organized in hashes, the operating system actually make the page available to all places in the physical memory locations. So it's actually a fully associativity cache, right? If you treat the virtual memory abstraction in this way, you will find it's pretty similar to the idea of cache in computer architecture. So we can talk more about the address translation in the next lecture. But before you leave the classroom, there are several things that I want to let you know. First of all, we have assignment 2 due this Wednesday, and we will have a midterm next Monday. Some of you start asking that. This is an in-person class, so I suppose the exam will occur in person, and I haven't done any in-person exam for a while, so it's a cultural shock for me for sure. I know it's a cultural shock for you as well, right? So to alleviate that cultural shock, I will release a sample midterm this Wednesday. And it's always a good idea to release a sample midterm because the better your grades is, the easier our grading is, right? So, and again, if you want to start it right now, it's not a bad idea. And just focusing on the topics we covered in the lectures, apparently the performance evaluation and the memory hierarchy, right? And we are going to cover topics that we are going to talk about this Wednesday, and what I can tell you is going to be on this Wednesday will be the virtual memory part as well as some very basic 5-stage pipeline in modern processors. So project will be up by the end of the week. So those are the things that I can let you know. Other than that, enjoy the rest of the day. If you have any other questions, we have all hour to.
It makes sense. Yeah, like Windows.
Also, it doesn't work.